So this feedback video we will have a quick look at how all the forces actually tie together and focus a bit on some questions which you had on the propulsion and the mass flow. And there were also some questions about equivalent and true airspeeds which we will look at. But to really explain it to you I need a blackboard, so let's go inside and find the lecture room and I can show you a few helpful tips for the test and for the exercises. So there was only a limited way, a limited set of ways in which we can make assignments. And I want to show you how all the forces tie together to show how basically everything is connected and that in the end even exercises which might look very different are still very similar. Often we start off with giving you the weight. So if we have an airplane here, then we have the weight, which is the mass times the gravity acceleration, which in stationary flight is equal to the lift, L, for which we had the formula CL, the lift coefficient, times half rho V squared, the dynamic pressure, times the area of the wing. Well, this lift is generated at a cost, which is the drag, and this relation is often given. The CD as function of CL is given, for instance, CD0 plus CL squared divided by pi times the aspect ratio of the wing times the Oswald efficiency. In this way we get the CD, which allows us to calculate the drag force, which is the same equation as the lift, but then with the drag coefficient. So times the dynamic pressure, half rho V squared, times the wing area. So if we go from weight to lift to drag, then we also have solved the last force, which is the thrust force, because that's equal to the drag. In stationary flight, as lift is equal to the weight, the thrust is equal to the drag. So you can use that same equation to calculate the thrust. And for the thrust, of course, we also know that it is, from the propulsion lecture, it is the mass flow times the jet speed minus the initial speed of the air when it enters the engine. And this initial speed, of course, is basically the true airspeed, which you also use in this equations, the V. If you just have the V for velocity, this is the true airspeed. Well, this mass flow, there are other ways to find it except for this one. And that is, for instance, by using the diameter of the engine inlet and the speed and the density. So imagine that we have a certain engine inlet, this shape with a radius, and this inhales air, and for a certain amount of time the thickness of the cylinder of air that will enter the engine is basically given by the thickness is given by the true airspeed times the time step, the delta T. And of course the amount of air that goes in there, if we want to know the mass flow, we can first see the volume of this disk, which is then the area here, which is pi times r squared, or if we have the diameter, we can also say d squared divided by 4. These are the two equations for the area. One of them you can use, and then the total volume is given by this area, so p r squared times v times delta T. And this is a volume. If we multiply this by the local density of the atmosphere, we have basically the mass flow in a certain time delta T, or per second we basically have also the mass flow here. Rho times the area of the inlet times the true airspeed, and this is the atmospheric rho, is another way to find the mass flow for an engine, which we can then use in our equation for thrust. So this was the first hint I wanted to give you. So, except for how it all ties together, another way to calculate the mass flow is using the area of the inlet, and for the thickness we use the speed, because we want to look at only 1 second, multiply it by the density of the atmosphere, and you will find the mass flow. Then there was also a question about equivalent airspeed and true airspeed. I mentioned the dynamic pressure here. The dynamic pressure is what the aircraft feels with its drag and the lift, but also with the instruments. And this dynamic pressure, the speed scale is based on that using this equation, half rho v squared. From having the half rho v squared, we can calculate the v, but this is calibrated at sea level, so for the rho 0, and we call this the equivalent airspeed, but at sea level it's the same as the true airspeed. But later on we assume that only the speed changes, while actually, of course, the total dynamic pressure is then given by half rho v squared, and this is then the true airspeed. And both the speed and the density varies, but to keep it simple, we assume that just the speed changes, which means that this is always true. The dynamic pressure is always given by half rho 0 times the equivalent airspeed, and it's the same as half rho times the true airspeed. And this also shows how you can calculate one into the other. For instance, if we have the equivalent airspeed and we want to know the true airspeed, then by taking the square root on both sides and getting rid of the half, we find the relation between the equivalent airspeed and the true airspeed. And then here we have the rho's. But which one is now the rho 0? Well, it's easy to remember that rho 0 always has to be multiplied with the equivalent airspeed. So in this case, this is the rho 0 and this is the rho. And this is the way to calculate it. And of course, if you have to go the other direction, these two invert and they go on this side. But this is how to get from equivalent airspeed, as you see it on the instruments, as it is important, if it's often given, if the stall speed is given in equivalent airspeed, to get to the true airspeed, which is the real one, which you use in all these equations. Of course, instead of using half rho times the true airspeed squared everywhere, you can of course also use this, as long as you then use the air density at sea level. But for these kind of equations, the mass flow, you always have to use the true airspeed and the true air density.